So today I will be presenting about solid-state NMR of materials. Nowadays, material means many areas will come into picture. I have given importance to the organic materials. In few cases, other clay which are NMR active is also shown. My main area is thermotropic liquid crystals, as a few minutes back I was introducing to you. I have been using solid-state NMR right from the 1990s. So the advancement in the solid-state NMR is breathtaking. Solution NMR has played an important role in many areas of research. Physics for developing the new pulse techniques, chemistry for routine. Synthetic chemists cannot dream his research without solution NMR. In material science, especially when you have a amorphous material or cross-linked systems, solid-state NMR comes to the picture. In biology, today, one of the most active areas of solid-state NMR is biology. So, today's presentation, I will be covering a few basics of NMR. I understand that there are two speakers who are going to deal with NMR, so I'm going to touch only essential part of it. Then solid-state NMR, why solid-state NMR is different from solution NMR, applications of solid-state NMR to materials. So this is a general introduction to spectroscopy. Spectroscopy is generally defined as interaction of electromagnetic radiation with matter. Spectroscopy deals with interaction of electromagnetic radiation with matter. The spectroscopy is broadly classified into absorption spectroscopy and emission spectroscopy, also classified as atomic spectroscopy and molecular spectroscopy. NMR comes under molecular spectroscopy because we derive the molecular structure from the NMR spectrum. On the right side of the slide, you can see process of absorption, where when the matter is allowed to interact with electromagnetic radiation, when it absorbs the energy, system goes to the excited state. We know that thermodynamically excited state is not a stable state, so it prefers to come back to ground state. The excess energy will be released in the form of heat. In the case of emission spectroscopy, it is almost reverse. Here, the matter is supplied energy in the form of heat, not in the form of electromagnetic radiation. Here also system goes to the excited state, but an excited state is not stable, comes back to ground state. Then the excess energy is released in the form of electromagnetic radiation. The classic example for emission spectroscopy is that flame test, what we normally do. For example, barium containing salts, if you expose to the flame, you can see brick red color. That's because of emission spectroscopy. In all the cases, we have to have two states, ground state and excited state. Ground state is lowest energy, excited is the next highest energy. So the difference between ground and excited state is expressed as a delta E, which is nothing but energy difference between E2 and E1. When we come to the basic principles of NMR, we all know that electron, proton, and neutron are considered as subatomic particles. They have minimum two common properties, in some cases three. One is the spin, other is the charge, and another one is the mass. So in case of neutron, we don't have charge, but it has mass and spin. According to theory of electromagnetism, when a particle associated with spin, charge, a particle associated with charge undergoes spin, it behaves like a bar magnet. So what is bar magnet? You take any magnet, it will have two poles. One is north pole and south pole. So essentially, the electron, proton will behave like a bar magnets because they are associated with charge and spin. Now, if you see periodic table, all the elements, all the nuclei are not NMR active, only some are NMR active. what is the basic criteria to identify whether a nuclei is NMR active or not? Is looking at the atomic weight and atomic number. So from that you can find the spin quantum number. The spin quantum number can be 0 or non-zero. In non-zero cases, we have 1/2, 3/2, 5/2, or it can be 1, 2, 3. So, for example, you take most frequently used nuclei, proton, carbon-13, P31, or spin-off nuclei, deuterium, which is isotope of hydrogen, and nitrogen, or spin-1 nuclei. So, deuterium and nitrogen will have are classified as a quadrupolar nuclei, whereas the other things are bipolar nuclei. Now, this is a schematic representation. For example, if you have a NMR tube, which is shown like this, so put under in the magnetic field represented as B0, you can see the orientation of tube versus the magnetic field axis. Then use radio frequency oscillator. Then when radio frequency oscillator hits the sample, resonance takes place. You get absorption spectrum, which is nothing but the chemical shift versus the intensity. So it is a 1D plot, x-axis chemical shift, y-axis is the intensity. Now, what is resonance? Actually, when you use radio frequency as input energy, when the molecule, see for example, if you take a methane CH4, it has 4 protons which are chemically equivalent, so you expect one signal. But most of the cases, molecules will not have same kind of chemically environment protons. It will have different environment, so we expect different signals. In such cases, the precisional frequency, which is nothing but the proton frequency in the magnetic field, it equals to radio frequency, which is represented as HU and HU dash. H is the Planck constant, mu is the frequency of radio frequency, mu dot is the frequency of proton, which is the magnetic field. When HU is equal to HU dot, then the signal comes. So when you get a signal, it gives an indication that it is under the resonance. What is under resonance? The sample is under resonance. That is, the proton is in resonance with the radio frequency. That is the reason why it is able to absorb the energy and you get a signal. Now, if you look into these parameters, first of all, why a chemist is more interested in NMR. So in organic chemistry, when you talk about inductive effect and hybridization, so these are some kind of properties which are determined by the electronegativity and electronegativity of electron releasing and electron withdrawing groups. Especially inductive effect comes into the picture when we have a CC single bond systems. We know that hybridizations are possible in at least organic molecules 3 times, sp3, sp2, sp. So when you have these factors coming into the role, then the chemicals also vary. So the general range for proton is 0 to 20 ppm, carbon-13 is 0 to 220 ppm. In that sense, carbon-13 has broader window, proton has narrow window. Then what is the relaxation? Actually, a few minutes back, we talked about the excitation. When a system is under excitation, thermodynamically it is not a stable state. So it comes back to ground state. While coming back to the ground state, excess energy is released. So the process of releasing the excess energy is classified in NMR into 2 parameters. One is spin lattice relaxation, another is spin-spin relaxation. The question is that why systems should lose the energy? According to law of conservation of energy, so input energy and output energy has to be same. So when excess energy, when system is coming back to the ground state, the excess energy will be released in NMR. This process takes in the form of T1 and T2. Now, how to run the spectrum? Generally, in solution NMR, when a sample is dissolved in a particular solvent, preferably deuterated solvent, because all these spectrometers are now deuterium locked. Unless you use the deuterium solvent, you cannot run the NMR. Then we have an internal standard known as tetramethylsilane. And under these conditions, if you prepare a sample and give it to the operator, he will run the spectrum. So now, why proton NMR, or for that matter, any NMR, is important? So 3 points are, especially for proton NMR, are important. One is the chemical shift. Second is this coupling constant. Generally, it is known as a scalar coupling constant. Then integration. Integration means intensity of given particular signal. So in spectroscopy, intensity is indirect measurement of population of the particular state. So these three parameters you can get from NMR. Each parameter has its own contribution. Now, what is chemical shift? In the initial phase of NMR, there was a confusion how to represent the precision frequency of nuclei. Then they found a method where by using tetramethylsilane, whose chemical shift value is taken as 0, then by using this particular equation, you can find out the delta, which is nothing but chemical shift. In present day NMR spectrometers, you don't have to worry about all these VXL, VTS, V0. You get the delta value in the x-axis, you can use for identification. Now, Vx is the precessional frequency of X, that means unknown nuclei. VTMS is the precessional frequency of tetramethylsilane, and V0 is the operating frequency. So, NMR spectrometers are generally expressed here in terms of radio frequency, that is 300 megahertz, 400 megahertz, 500 megahertz, or in terms of Tesla. Tesla, the magnetic flux density is also represented in terms of Tesla. But most popularly, it is represented in the form of radio frequency. So when we talk about NMR, people say that 300 megahertz, 400 megahertz, 500 megahertz NMR. Now, I would like to introduce the same concept in a different form. For example, if you take a cubic lattice, this is nothing but a sample which is in the cubic lattice compartment. In the normal conditions, that means in the absence of magnetic field, because of Avogadro number, we have more number of nuclei in a given sample. Each nuclei will act as a kind of a bar magnet because it is associated with the spin and energy, spin and charge. But all these protons are in different orientations. What is orientation? For example, if you see arrow here, it is in this direction. The second one is in different direction. Third one is in different direction. Fourth one is exactly different direction. So this is known as random orientation. In the absence of magnetic field, the nuclei will have random orientation. But if you put under magnetic field, which is known as external magnetic field, represented as B0, which has north and south poles, now the same compartment, the cubic compartment, the samples will have two kinds of orientations. This is known as field-induced orientation. Because of the field, the orientation is coming with the picture. Now, this is also represented in the above here, B0 applied magnetic field. If you take a spins, we have two possibilities. One is north pole up, represented as a plus half, north pole down, represented as a minus half, also represented as alpha and beta state. So that means degeneracy has come into the picture. So one state we can take as a ground state, another state we can take it as an excited state. So now if you see the next slide, we know that the Zeeman effect or Zeeman interaction, that means splitting of spectral lines in the magnetic field is known as Zeeman interaction. Now, since our measurements are being taken in the presence of magnetic field, the alpha beta, which we discussed a few minutes back, we have two different populations. So alpha can be taken as a ground population, ground state population, beta as higher excited state population. So what actually this picture shows is that a slight excess of molecules in the ground state. So there will be some populated in the excited state also, but the population of the alpha, that is ground state, is more in the presence of magnetic field. When you remove the magnetic field, the orientation will be like this, so alpha beta states will not exist. So essentially, magnetic field is important for running the NMR. In the absence of magnetic field, NMR phenomena will not take place. So this is pictorially represented. One energy state is getting split into two energy states because of applied magnetic field. They can be termed as alpha beta or E0 E1 or E1 E2. So this delta E difference is actually suitable for radio frequency. That's why in NMR, radio frequency is used for exciting the protons. Now, the precisional frequency, which we talked about each individual proton, is related to these particular factors. In this, most of them are constants. So what we have to worry is that the external magnetic field is directly proportional to precisional frequency. That means if I run 100 megahertz, 300 megahertz, 500 megahertz, or 700 megahertz, it is implicit to say that at higher magnetic field, the precisional frequency values will be high. So the resolution of the spectrum goes up so that signals which are very closely spaced in 100 megahertz become separated because the precisional frequencies are different as the magnetic field is different. So these are the fundamental aspects of the nuclear magnetic resonance spectroscopy with respect to proton. Now, how do you run NMR? So if you go to any NMR facility, if you enter the NMR room, you can easily find this kind of components. So the first one is the external magnetic field. Today, superconductors are used for generating magnetic field. Normally, liquid helium and liquid nitrogen are essential because the superconductor, that alloy, behaves like a superconductor when it is soaked in liquid nitrogen or liquid helium. Then we have a NMR console. It is like our PC console. Then we have a monitor. So after putting a sample inside the magnet, see the sample compartment is shown, which is nothing but part of the probe. This is solution NMR probe. For solid state probe will be different. So once you put the sample inside the magnetic field, then through computer we can control the pulse. First we can run the proton NMR. If you are happy or if you are satisfied with the spectrum, you can immediately run carbon-13 NMR also. This is generally done for organic molecules where proton and carbon-13 both are part of the nucleus, part of the molecule. Now, what is high-resolution solid-state NMR? Why should we worry about this particular technique? Usually, in solution NMR, all the molecules, the associated protons, will have more degrees of freedom, which means that it has translation motion, rotational motion, vibrational motion. Anyway, electronic motion is always there. So, because of the translation motion, the molecules move from one place to another place. As a result, this is something like a tumbling. Molecule tumbles. When molecules tumble, whatever anisotropy is present in the molecule, that gets averaged out. As a result, you get very sharp lines both in proton and carbon-13 NMR in solution NMR. Unfortunately or fortunately, in solid-state NMR, the signals are very broad. Now, what is the reason for that? In solid state, generally, when you take an amorphous system or a crystalline system, the translation motion is restricted. So what are all possible is rotational motion may be there, may not be there. Vibrational motion is allowed. So when translation motion is restricted, the spins which are part of the molecule will experience different kinds of environment, different kinds of interactions. One of the most important contributions for line broadening in solid state NMR is dipolar broadening, which is given here. Now, this can be eliminated by dipolar decoupling. Dipolar decoupling is the technique. Dipolar broadening is the factor which contributes for dipolar interactions, which I will explain after a few minutes. So, second thing is the chemical shift anisotropy. Generally, in solution NMR, you get for each nuclei, which is chemically same environment, one chemical shift. But actually, the one chemical shift is contributed by three chemical shifts like sigma XX, sigma YY, sigma ZZ. Because of tumbling of the molecules in solution, all these three different chemical shifts get averaged. So what we get is an isotropic chemical shift. But in solid state, as I mentioned, the molecular translation motions are restricted. So each one starts contributing. That means sigma XX, sigma YY, ZZ will contribute for broadening of the line. So that is known as chemical shift anisotropy. What is anisotropy? Anisotropy is a property which changes direction. Since the chemical shift is changing here, we call it as a chemical shift anisotropy. This can be effectively handled by using a technique known as magic angle spinning. Then another problem, especially for carbon-13. For example, if you see here, the fundamental properties of proton and carbon-13 decay. Proton natural abundance is 99.98, almost 100%. The gyromagnetic ratio is 267.5 to 10 to the power of 6 times of radians per second per Tesla. Proton spin quantum number is half. Now come to the carbon-13, the natural abundance is 1.1. So compared to proton, the carbon-13 natural abundance is only 1%. Another problem is the gyromagnetic ratio, which is 67.28, 10 to the power of 6 radians per second per Tesla. So the ratio between the proton and carbon-13 gyromagnetic ratios something like 4 times. So if you want to find a nuclei of carbon-13, the amount of time what you do for proton has to be minimum 4 times higher than proton. Second point is the gyromagnetic ratio is also low. However, the spin quantum number is off. For your kind information, carbon-13 is isotope. It is not a natural element. So the natural abundance is low since carbon-12 is 99.98, 99%. Carbon-13 is only 1.1%. Carbon-12 is NMR inactive. Carbon-13 is NMR active. So if you want to run carbon-13 NMR spectroscopy, so you have to spend more amount of time, and also especially for solid states, some other techniques will come into the picture. Now, if you want to see the solid state NMR of glycine, which is the simplest amino acid consisting of amino group, methylene group, carbonyl in the form of carboxylic acid. Even for such a aliphatic consisting molecule with simplest possible structure, you can see the signals are very, very broad. For example, if you take 50 to 250, this is the scale normally used for carbon-13 NMR, so you cannot make out anything. One may say there is a broad signal here around 50, below 50, and there is another broad signal at 180. So this will not give any information useful for extracting the geometry or structure. Now, in order to handle, that means in order to enhance the signal intensity, there are new techniques which came into the existence. Among them, if you see here. So what actually I'm trying to say, if you want to get well-resolved carbon-13 NMR of a crystalline or amorphous solid, you need to handle these 3 issues: dipolar broadening, chemical shift anisotropy, low signal to noise ratio. Now, in order to handle these 3, you have to employ these 3 techniques. That's why high-resolution solid state NMR is nothing but DD, CP, mass NMR. Now, what are dipolar broadening? Now, mind you, we are all discussing these interactions in the presence of magnetic field. Now, each proton is endowed with dipole. This is known as a magnetic dipole. Then we have another proton which is nearby to this particular proton. That is also magnetic dipole. When these 2 magnetic dipoles interact, for example, you take a small magnet, that magnet which children use, you bring another magnet nearby to that, then there are 2 possible interactions. One is the attraction, another is the repulsion. So similarly, when 2 spin systems come close to a particular distance, then we have interactions coming into the picture. Now, such interactions are known as homonuclear dipolar couplings, proton-proton homonuclear dipolar couplings. That interactions lead to interactions are termed as dipolar couplings. These dipolar couplings contribute for line broadening in solid state NMR. Then we have carbon-13 proton heteronuclear dipolar couplings. That means carbon-13 is also NMR active, proton is also NMR active. When they come nearby to particular distance, they will have interactions. They will contribute for dipolar broadening. So dipolar broadening can be classified into homonuclear dipolar broadening, heteronuclear dipolar broadening. So these 2 will contribute for broadening of the line. Now, when you talk about homonuclear dipolar broadening, this is more dominating feature because the natural abundance of the proton is high. The gyromagnetic ratio is also high. Whereas in the case of carbon-proton heteronuclear dipolar coupling, we have 1 99.98% natural abundance, another is only 1%. Also, gyromagnetic ratios are different. So the contribution of heteronuclear dipolar coupling is relatively less compared to the homonuclear dipolar couplings for broadening of a line in solid state NMR. Now, the dipolar couplings, what we are discussing, are represented in terms of a symbol known as D, generally represented in terms of kilohertz. Whereas scalar couplings, what we measure in solution NMR, are known as scalar J. J is the symbol for scalar coupling. Their magnitude in the range of hertz. So what is hertz? Hertz is 1 cycle per second, CPS. Earlier scale was CPS, now it is converted into hertz. So scalar couplings, the magnitude is hertz. Dipolar couplings, magnitude is in kilohertz. Because of dipolar couplings contribution high for broadening of a signal in solid state, so the dipolar couplings contribute for line broadening more. Then, as I mentioned, the chemical shift is 3 components. For example, you see sigma XX, sigma YY, sigma ZZ, 3 components of a chemical shift. In solution, because of molecular tumbling, all 3 gets averaged out, so you get del sigma iso. Whereas in the solid state, in the presence of applied magnetic field, we have a polycrystalline powder. I am not talking about a single crystal. I am talking about an amorphous solid or a polycrystalline powder. Now, here, if you see this powder, orientation is parallel to the magnetic field. This makes some angle with respect to magnetic field. This makes another angle with respect to the B0. As a result, the signals are getting separated. For example, this contributes for this contributes for this, and this contributes for this. When you have so many kind of orientations in a given sample, you get so many signals. That means each orientation contributing for a signal, so you get a powder pattern. This is nothing but a powder pattern of a chemical shift. So this chemical shift will not be of use since we are talking about sigma iso. So what we need is isotropic chemical shift. So how to get rid of this anisotropy? So why this we call it as anisotropy? So if you see here, there is one signal here, one signal here, one signal here, but inside there are so many signals. Now, how come this powder pattern is coming? This powder pattern is contributed by sigma XX, sigma YY, sigma ZZ. Now, where is the isotropic chemical shift? When you average this will be the sigma iso. In solution NMR, we get sigma iso, whereas in solid state NMR, we get a pattern which reflects about these 3. Now, if you want to get sigma iso in solid state NMR, you have to go for magic angle spinning. What it does. So, a scientist by name Andrew introduced in 1958 a method where solids can be mimicked to get solution kind of situation. So, in NMR, the B0 represents the magnetic field. Now, if you take a sample rotor, which makes an 54.7 known as magic angle, and if you put your solid sample inside the rotor, whether it is a polycrystalline sample or amorphous, if you rotate with the different spinning speeds, then the chemical shift anisotropy slowly breaks down, and finally you end up with isotropic values. For example, at 0 kilohertz, that is without spinning the sample, we have a very broad lines. At 2 kilohertz spinning, we have multiple lines. As the spinning frequency increases, when you reach the 12 kilohertz, we have 2 sharp lines coming from the glycine. One is coming from the carbonyl peak, another coming from CH2 carbon. In any case, NH2 we cannot see. We are not talking about the nitrogen NMR. We are talking about the carbon-13 NMR. So these 2 chemical shifts and these 2 patterns are exactly like your carbon-13 solution NMR. So you can see small humps here. Those are known as spinning side bands. Actually, the spinning side bands will come into the picture when the spinning frequency is not able to kill the chemical shift anisotropy completely. Okay, so chemical shift anisotropy can be handled using magic angle spinning. Dipolar coupling can be handled through dipolar broadening can be handled through dipolar coupling, dipolar decoupling. Then what is cross polarization? Here I mentioned about the cross polarization. What is cross polarization? As I mentioned, if you see the natural abundance of proton and carbon-13, they are almost like In one case 100%, another case 1%. So since the proton natural abundance is high, gyromagnetic ratio is also high, there is a possibility that you can transfer the magnetization from proton to carbon-13 under certain conditions. These are known as Hartmann-Hahn condition or CP condition. In that condition, we can transfer effectively the spin magnetization from proton to carbon-13. So as a result, even though natural abundance of carbon-13 is low, because of magnetization, since it is something like a borrowing it. So since the carbon-13 nuclei borrows magnetization from proton, so sensitivity of the signal increases. Now this can be very easily seen in a spectrum here. For example, the polymethyl methacrylate, a thermoplastic polymer, known for excellent transparency. Actually, when you run normal conditions without applying any solid state techniques, you end up with a simple noise. There is no signal. When you use CP and high power decoupling, CP is nothing but cross polarization, that is transfer of magnetization from proton to carbon-13, also dipolar decoupling. So you see two signals coming which are still broad, and there appears to be a signal but is not resolved. Whereas if you see CP high power decoupling, so these two signals become sharp, but third signal is not evolving. But when you apply everything, that is dipolar decoupling, cross polarization, and magic angle spinning, you can see beautiful spectrum coming from all the carbons of the polymethyl methacrylate. It is one of the classic demonstration of a thermoplastic polymer whose NMR cannot be run in solid state earlier. By using these these high resolution solid state NMR, people are able to completely resolve carbonyl, backbone methylene, backbone non-protonated carbon. Then we have, that is quaternary carbon, alpha methyl, and OCH3. So OCH3, CH2, quaternary carbon, CH3, CO, all have been resolved. So in order to get this kind of spectrum, we have to have dipolar decoupling, we have to have cross polarization, we have to have magic angle spinning. Today, any 1D solid state NMR invariably involves all these three factors, all these three elements to get a resolvable spectrum, which can be used for structure identification or for geometry information. Now, this is one of the oldest slide I have been using. This is known as a 4-chlorophenylacrylate polymer, phenyl ring containing system. It is a solution NMR run for the sample dissolved in CdCl3 solvent. For the sake of clarity, CdCl3 signals are removed here. Then we have a homopolymer which is in the solid state, CP mass NMR. Then same polymer is cross-linked with the divinyl benzene, a cross-linking agent. You can see how the line widths are changing even with high resolution NMR. So you can see the phenyl ring carbons coming here, ester carbonyl here, and backbone methylene carbons coming here. Now in the case of solution NMR, there is a broadening here, that is because of tacticity. So using high resolution solid state NMR, signals which cannot be resolved can be resolved, so that we have a evidence for our substance which is not possible to dissolve in any solvent. For example, cross-linked polymers are not soluble, you cannot melt them. So the only way to do the NMR is solid state high resolution NMR. In fact, Jacob Schaffer in mid-80s did a lot of work using polymers, measuring the structure above the glass transition temperature and below the glass transition temperature, including rotational motions. Now, another polymer, poly-NXL glutamate. Here I am showing how variable temperature NMR can be measured, starting from -100 degrees to 80 degrees centigrade, where the signals which are appearing as a 2 becoming 1 here, because the dynamics are coming into the picture. So today, variable temperature high resolution solid state NMR has become a routine technique. If you specify the temperatures people are willing to do the 1D experiments, from that you can find out where the signals are getting separated, what temperature signals are getting separated, what temperature signals are getting coalesced. Another important application is polymer blends. So here I am showing the polystyrene polyvinyl methyl ether blends. These are very commercially important systems. You see polystyrene NMR, you have backbone methylene, styrene. Then we have aliphatic signals coming from polyvinyl methyl ether. In the blend, you can see the presence of both. Since it is a 5:5, that is 50-50 composition, we can the contribution of these two. So one can easily identify when a given plastic is given to you, you can identify what are the components present in the system. This is a natural polymer. In fact, currently the high crystalline cellulose is gaining a lot of importance because it's a natural resource. So in crystalline, in NMR, crystalline systems will give short signals, whereas amorphous will give very broad signals in spite of applying high resolution. The reason is that in crystalline systems, we have long range positional and orientational order. In amorphous systems, order is not there. This order contributes for better signal to better spectral resolution. So here I am showing the cellulose signals. You can see because of the separation of the signals, well resolution of the spectrum, you can easily identify all the carbons in the system. So another important area where carbon-13 NMR is gaining importance is solid-state polymorphism. So when you take molecular crystals like 2-amido-2-nitroestranilide, they can exist in different forms. There are cases even at room temperature, we have alpha form, beta form, gamma form. So this particular polymorphism, solid-state NMR is one of the best way to identify at given temperature what kind of polymorph is present. Is it an alpha form, beta form, or gamma form? So if you see these signals here, one with hydrated sample, that is water, then we have a different colors. So if you see here, the signals which are sharp with the hydrated form are becoming broad, especially in this case. So using not only that, this 1+5, that means the signals are also getting shifted because each polymorph will have different kind of orientation. We have a different signal coming from that. So for example, you take a mortar, you make a fine powder. So if the polymorph is changing, then you can find out from the NMR whether the same based on the signals, you can find out whether we have a same polymorph or other polymorph coming into the picture. Here, another important polymorph is being discussed. This is 2-thiobarbitric acid. In organic chemistry, wherever keto group is there, adjacent level protons are there, we have possibility of keto-enol formation. So this is a keto form, enol form. So this molecule can exist in different forms, keto form and enol form. So you can find out the kind of 9 combinations are possible. Looking at the NMR, solid-state high-resolution carbon-13 NMR, you can find out which is dominating. For example, if keto form, the signals which are coming at 180 will either completely vanish or shift. The OH signal, which is not there in the keto form, this carbon, because of the double bond and OH, will start appearing. In this spectrum, the carbon-13 NMR, some star signals are there. Those are coming from spinning side bands. So for spectral interpretation, basically they are low intense, so you can ignore. On right side, first time I'm showing the proton NMR of solid state under high resolution solid state conditions. You can see even with the high resolution, that is spinning the sample at 32 kilohertz, still the signals are broad. However, we can identify hydrated form versus form 2 based on the number of signals appearing and the corresponding permutations also. So high resolution solid state NMR has become a standard tool for identifying polymorphism in solid states, both for the biological systems, molecular systems, and macromolecular systems. Another important contribution of high resolution solid state NMR is a drug, especially pharmaceuticals. Nifedipine is the drug which I am showing here. This is the carbon-13 NMR of a crystal form and amorphous form. You can see in amorphous form, even though molecular structure is same, the signals are becoming broad. So when signals become broad, sometimes there is a possibility of signals getting buried because the line width is going up. Whereas in the crystal form, you can see beautiful resolution, so very well resolved carbon-13 NMR. So by looking at the spectrum itself, with not even examining the sample, you can say the drug is in the amorphous form or crystalline form. So another important contributions, recent contributions of high-resolution solid-state NMR in the field of glasses. The glass is an amorphous solid. It is usually applied to inorganic solids, not to plastics or other organics, and they do not have a crystalline internal structure. They are usually hard and brittle solids. So if you take mesoporous bioactive glass composition, which I extracted from a reference given here. So if you see the stoichiometry, calcium, silicon, phosphorus, oxygen are present here in different stoichiometric ratios. Then depending upon the composition, we have Q2, Q, different Q, that is sites information is also possible. So here, using the solid-state NMR, calcium NMR is possible, silicon NMR is possible, phosphorus NMR is possible, oxygen NMR is all possible. But oxygen and calcium NMR are more difficult compared to silicon and phosphorus NMR. Silica is also spin quantum number off, phosphorus also spin quantum number off, oxygen, calcium little difficult. So generally people use silicon, phosphorus to find out what kind of sites are there, how the sites are getting distributed. For example, if you see P31 NMR here, we have two ranges, the chemical shifts almost near zero and chemical shifts above zero values. So based on the P31, since we have phosphorus here, based on the P31, based on the chemical shift values, we can identify whether it is a Q 2.8, 7.2, something like information which is part of the glass, you can find out. In the case of silicon, for example, if you see, the compositions are given here, S58, S75. So when signals, even employing the silicon mass NMR, you can see the signals are not completely resolved here. So in such case, a deconvolution is possible. So in the deconvolution, wherever these shoulder splits are there, you can do deconvolution, identify the chemical values, and silicon, the values are going normally into the negative values because tetramethylsilane is taken as a zero. So silicon is electropositive. That's why the signals are going with zero or sub-zero values. In the case of zeolites, in the contemporary literature, zeolites are often used for many processes. So they are very good natural mineral materials and mostly hydrated aluminosilicates. Presence of sodium, potassium, calcium, barium is also possible. They can be readily dehydrated or hydrated and used as a cation exchanges or a molecular sieves. In such cases, using aluminum NMR, aluminum is the 5/2 is the spin quantum number, we can identify hydrated versus dehydrated system. So you can see these two here, zeolite ammonia that is treated with ammonium acetate, beta, dehydrated zeolite, ammonia hexafluorosilicate is used for dealumination. So using the spectrum, you can see the 13 is the chemical shift, T4, 32, and when hydration is becoming, and in beta state, that is beta case, the resolution is completely lost. So another area where I am active is the NMR of liquid crystals. So for example, if you take a 4-hexyloxybenzoic acid, which is nothing but a molecular crystal, it melts at 105.4 degrees centigrade and clears at 153.2. You can see solution NMR, all these peaks are completely resolved. Now, in the case of solid-state NMR, using DDCP mass, the signals are comparable with solution NMR, even though residual broadening is there. Another important feature, instead of 3 signals here, we see 4 signals, additional splitting coming into the picture. But in the case of liquid crystalline phase, that means when you melt it above 105, the signals are getting completely changed. One is resolution is increased, sharpening of the signal taken place, chemical shifts also changed. Because this is happening because the orientation of the molecule is changing in liquid crystalline phase because of the liquid crystalline properties. So using solid-state NMR, one can run the high-resolution spectrum. Since these are liquid crystal molecules, that means orientationally ordered fluids, you don't have to run mass. DDCP is enough. Whereas in this particular case, you have to run DDCP mass because it is a polycrystalline sample. Now, you can also use 2D NMR for getting the orientational order, geometry, molecular structure. Here, the basic difference between 1D and 2D is that in 1D NMR, x-axis we have chemical shifts, y-axis intensity. Normally, intensity is not shown. So, because we have integrals, computer-generated integrals are there. In 2D NMR, x-axis will give one particular information, y-axis will give some other kind of information. So, in this particular spectrum, you see heteronuclear dipolar couplings, carbon-13 proton dipolar couplings in the y-axis, carbon-13 chemical shifts in the x-axis. In 2D, the signals are normally known as contours because it's a slices of a 2D signal. So based on these contours, we can identify the structure of the molecule. One important point here is that carbon 17, 18, 19 are showing very high carbon-13 proton dipolar couplings compared to all other systems. That clearly indicates that 17, 18, 19 are coming to the center of their ring. So such information is clearly possible using high-resolution 2D solid-state NMR measurements. Now, I have not covered two important points because of the paucity of time. Also, complications associated with the subject. One is the molecular motion. You can find the molecular motion of a amorphous system or a polycrystalline system using T1. T1 is spin lattice relaxation. In the case of polymers, you can find this chain segmental motion or overall tumbling. Main chain motion, side chain motion can be easily mapped using spin lattice relaxations. Another set of experiments which have become very powerful in recent days, known as 2D solid-state NMR experiments, heteronuclear correlation spectroscopy. For example, in our system, if you have carbon and proton, most of the organic molecules will have carbon and proton. In order to differentiate non-protonated carbon, protonated carbon, one can run NETCAR experiments based on the contours. You can find out the chemistry values of the carbon proton. You can also identify whether the particular carbon is protonated or non-protonated. Multiple quantum magic angle spinning is routinely used, especially in case of aluminum containing systems, rotational echo double resonance systems, RAPGAR, transfer of population double resonance systems. Pulse sequences are also possible. Actually, in the dipolar decoupling, we are irradiating the proton frequency using second channel. That's why the dipolar decoupling takes place. Instead of completely decoupling, if you recouple some of the information, the nuclei are allowed to recouple, we have additional information which is not normally possible from routine techniques. Because of that, the solid-state NMR has become de novo technique in the current research, straight from molecular, macromolecular, supramolecular, and biological systems. So this technique can be used for mapping the structure and geometry. So I would like to conclude my presentation by thanking Satyabama University for giving the opportunity, especially to Dr. Reddy and CSIR CLRI, all the work I have carried out more than 30 years in CSIR CLRI, my collaborators in Bangalore and other places, my PhD students and my family members. For past 1 year, I have been working from home. So I would like to thank my family members for making the congenial atmosphere and on their support. And I conclude by thanking you for your patience listening. Thank you.